Welcome back to ECE 320A. We're in Unit 8 and we're doing the fun pieces or parts of convolution. And in this particular video, we want to talk about intervals and limits. And what we're trying to do is illustrate the difference between the time intervals, where y of t has a unique functional expression, and the difference between that and the integration limits that we need to compute those expressions for y of t. Here I've tried to illustrate that with this diagram. On the left, I'm trying to emphasize the intervals in which y of t might have a different functional value, and there I'm distinguishing between y sub 1, y sub 2, and y sub 3 in these different time intervals, or times where those functional expressions are valid, versus, and note that there's a not equal sign between these, the limits on the integration. And obviously the gammas don't equal taus, but in general, this gamma 3 is not going to be connected, or it'll be connected, but it won't be the same as what we're finding for these intervals that determine where those functional expressions might be true. And maybe over here, I would say that this is now our y sub 1, here's our y sub 2, and here's our y sub 3, potentially for these functional values of our y of t expression. So we're trying to now distinguish between intervals and limits, and we're going to do that by a few examples, or really one big example, which is this example here, where we're taking and convolving h of t with x of t, and I'll try to be consistent with my colors. And we've already looked at a video where we flip and get ready to slide, or prepare to slide x by creating x of t minus lambda. And so I'm assuming now that you are comfortable with progressing from x of t to x of t minus lambda. H of lambda is just a copy of h of t, with t replaced everywhere with lambda. And now what we want to do is in fact find the output of this convolution operation by examining unique overlap patterns when we're sliding x of t minus lambda by the choice of t. We're going to slide that x of t minus lambda from t equal to minus infinity, which is way over to the left, all the way through and proceed to t equal to plus infinity, or as far as we need to go to establish unique overlap patterns. And each time we get a unique overlap pattern, we'll need to compute the expression, the functional form for y of t. Let's now do that for this set of functions x and h. In this particular case, the first overlap, maybe I shouldn't call it an overlap because it's no overlap, but the first unique pattern is the no overlap case. And now what we want to do is establish when these intervals occur. That's what I'm meaning by pattern occurs when. And then we'll figure out how to compute y of t, which involves finding the limits on the lower and upper side of that integration operation. In this particular case, there is no overlap, but this pattern occurs when, hopefully you can see that that occurs when t minus 2 stays to the left of lambda equal to 0. So this pattern occurs as long as t minus 2 is less than 0. Or we can now say that y of t, which is the convolution integral, but the integrand is always 0 because the blue support interval and the red support interval do not intersect. This y of t is equal to 0 for t less than, if we add 2 to both sides, as long as t is less than 2, then we have no overlap. And you can see that here if you examined this particular system and said my impulse starts as soon as I hit the system at time 0 and it finishes at 4, now what I'm going to see is, oh, if I don't start hitting this system until 2, I shouldn't expect to see an output before time t equal 2. So when I hit this system at 2, I will immediately start to see something ringing in my system because h of t responds. If I hit it with an impulse at 0, it responds at t equal to 0. Likewise, this system better not be shaking or moving after the impulse response dies out 4 units of time after I've excited it at time 5. So I should be seeing my output y of t being non-zero between 2 and 4 plus 5, or 9. So let's see if that actually ends up being the case in this particular example. And in fact, we are validating that y of t is not equal to anything. It's 0. Well, it's equal to 0 for t values less than 2. Let's look at the next overlap pattern. This is what I'm calling a partial overlap. I haven't pushed the blue waveform all the way through the red waveform, and this pattern occurs, and now we need to start looking at when this is true, and that's going to be true relative to t minus 2, t minus 5, 0, and 4. So what is going to happen in this particular case? Well, we have a lot of different possibilities, so let's look at those. We could say that this pattern occurs when t minus 2 crosses over the value lambda equal to 0. So we know this pattern is true when t minus 2 is greater than or equal to 0. We could also say that, well, we also need t minus 2 to be less than 4. But we also know that t minus 5 needs to be less than 0. So let's look at the intersection of all of these different constraints. We have this constraint which says t is greater than or equal to 2. We have this constraint. If we add 2 to both sides, we see that t is less than 6. And this constraint says that t is less than 5. So if we look at the intersection of these, we could look at this on a timeline. We could say, oh, we know that it's true as long as t is bigger than 2. We also know that it's supposed to be true for t less than 6, and it's also supposed to be true for t less than 5. And now we need to take the intersection of all of those, which is really going to only happen when we're between 2 and 5. So this pattern exists as long as t is greater than or equal to 2 and less than 5. That's the interval when this pattern is true. Now we need to find out what is the expression for y of t over this interval of time t between 2 and 5. And the expression for y of t will be found by taking the functional values for the red curve, which is h of lambda, and the blue curve, which is x of t minus lambda. In this case, let me remind myself, the blue curve was of amplitude 4, the red curve was of amplitude 3, and that's their functional values in this overlap pattern. I've indicated that now. I have 3 times 4 d lambda. That's my integrand. I now need to establish where do I have crosshatching or overlap between the blue and the red hash marks. I've now hash marked the red, and I've hash marked the blue, And I now need to figure out in what interval, for what values of lambda, is that blue and red hashing overlapping. When do my support intervals overlap? And that's going to be true on the lower side when lambda is equal to 0, right here, and when when lambda gets up to t minus 2. My limits then on the integration are from lambda equal to 0 up to lambda equal to t minus 2. So that in this case I have 12 lambda, that's the integral of 12 d lambda, from 0 to t minus 2, or I now have 12 times t minus 2 minus 0, or y of t now is going to be equal to 12t minus 24, and that's true for that range of t. So in that interval from 2 to 5, I have this expression for y of t. And I hope it's clear that 2 is not equal to the lower limit and 5 is not equal to the upper limit of the integration process. So my intervals and limits are distinct or unique. That's for this particular pattern. Let's look at the next overlap pattern. And in this overlap pattern, what you typically want to look at or start being aware of is what's the length of my interval of support regions for the two waveforms. In this case, the x of t, which is of amplitude 4, has a shorter interval of support, or values of lambda where it's non-zero, versus the red interval. The red interval is now going to be, if I would do this properly, and it looks like I have made a mistake, so let's now put this back to 4, what it's supposed to be. Otherwise, my intervals would have been the same length. So now I have an interval for h of lambda of 4 in terms of the length of its interval of support, and I have an interval of support on the blue equaling 3. I now want to find out, when does this pattern actually occur? This pattern occurs as long as what? T minus 2 needs to be less than 4, and I need t minus 5 to be bigger than or equal to 0. And if I solve these now for t, or add 2 to this first one, both sides, I have t less than 6, and I have t greater than or equal to 5. So I've sort of done those in reverse, but now t needs to be bigger than 5, and it needs to be less than 6, and that's the intersection of these to establish this unique overlap pattern. And this is actually a complete overlap of the two waveforms. What's the integral? Well, the integrand is the same. It's now 3 times 4. It's just the limits are going to be different. Now I'm looking at, when is the blue hash the same as the red hash? And that's going to establish my limits of integration. And hopefully you can see that this is the interval where the interval of support overlaps, or I'm now going from a lower value of lambda equal to t minus 5 and an upper limit going to t minus 2. My limits of integration then are from t minus 5 to t minus 2. Or I'm now integrating and get 12 lambda, evaluating that at the upper limit of t minus 2 and subtracting from that the lower limit, which is t minus 5. I have 12 times lambda evaluated at the upper limit, which is t minus 2, minus lambda at the lower limit, which is t minus 5. The t's conveniently cancel, and I'm left with -2 plus 5, or that now gives me 3 inside here. These t's cancel. I have t minus t, and I'm left with y of t being a constant of 36, and that should be clear here. I just have this rectangle of width 3 and height 4 overlapped always within this interval, overlapped with this other rectangle, but they only overlap over a width of 3. So I have 3 times 3, and I'm now, oh, well, I really have 3 times 4, which is an amplitude of 12, over a width of 3 units. So I could find that by point multiplying these together, and at each point I see that I have 3 times 4, or a value of 12, and I now have that height of the product of h of lambda with x of t minus lambda over this width of 3. So now 12 times 3 gives me 36, and that's a way of checking this particular answer, and that's true as long as I keep t between 5 and 6. So there's another value or functional expression for y of t between a different set of intervals, t between 5 and 6. Now let's look at the next overlap pattern. Now this overlap pattern occurs when, now we need to slide t minus 2 beyond 4, and we need to keep t minus 5 less than 4. So that now, adding 2 to both sides, we need t to be bigger than or equal to 6. Adding 5 to both sides, we need t less than 9. So this pattern is true as long as t lives between 6 and 9, and we want to now find what is the expression for y of t, which is h of lambda, which has a functional value of 3, times x of t minus lambda, which has a functional value of 4. The values of the limits on the integration now are determined by where I have both blue and red hashing. So the lower side is now established as t minus 5, and the upper side is restricted to being a value of 4. Or my integral limits are now t minus 5 up to 4. This is now 12 lambda evaluated at the upper and lower limits of 4 and t minus 5. I now have 12 times 4 minus t minus 5. Or what's inside the square brackets is now minus t plus 9. And if I now scale that by 12, I end up with minus 12t, and 9 and 12 is a little bit more than 100, or it's now going to be 90 plus 18, or 108. And that's true as long as t lives between 6 and 9. And you could check this at the extremes or at the different limits. If you looked at evaluating this expression, y at 6, it better equal what you had in the last overlap pattern, which was a 36 value. So if we now look at y of 6, we would plug in minus 2 times 6 plus 108, or in fact, we knew that 108 was 9 times 12. So now we have 3 times 12 effectively, or we could say minus 72 plus 108 if we wanted to make sure that we were doing this properly, and that now ends up being 36, which is a good check on our work. Finally, we want to slide t minus 5 all the way past the rightmost interval of support for h of lambda, and this pattern now occurs when t minus 5 is bigger than or equal to 4, or this is now true as long as t is greater than or equal to 9. So that now y of t, there's no overlap, so the product of those two, h of lambda and x of t minus lambda, gives you 0. The functional value for y is 0 when t is bigger than 9. And now we have our final answer. We know that it's 0 as long as t is less than 2. It's 12t minus 24, and you could evaluate that at 2 and see that, oh, it is actually equal to 0, so we do have continuity at the limits of my intervals. It's then 36, so if I evaluated that at 5, I would have 5 times 12, which is 60, minus 24, which is 36, so we're looking like we're consistent with our values or functional forms for y of t. It's then minus 12t plus 108, and that's true for t between 6 and 9, and it's 0 as long as t is bigger than 9. And as I said before, y of t is not equal to 0 between 2 and 9. And we could check that by looking at our very first functions, x of t and h of t. H is an impulse response that when you hit it with an impulse, it starts at 0 and stops at 4. We're starting it to hit it at 2, so we don't have to wait beyond 2. So we're going from 2, and then we quit hitting or shaking the system at 5, but it takes 4 more units to finish shaking, so we should be going between 2 plus 0 for time and 4 plus 5, or that should be non-zero between values of 2 and 9. And I won't leave that there because people would wonder what that corresponds to relative to this final result. But in the final analysis, we have seen that the actual expression or final answer does, in fact, is consistent with that observation. Another observation to keep in mind is that overlap doesn't mean that the functions both have to have the same sign. Overlap means that the intervals of support for x of t minus lambda and h of lambda overlap. Let's look at an example of that. Here, let's say that we've flipped and slid the blue, and now we're looking at a particular pattern, and we want to find what y of t is equal to. And now it's a little bit more involved because the red function actually has unique functional value over different parts of the blue waveform. The blue waveform, which now is the x of t minus lambda, that's the one that I'm now sliding. That now has a functional form of minus t plus lambda plus 2. Again, our variable of integration is lambda, and our adjustable parameter is t. And we want to now know, how do I find the value for y of t? And then we'll figure out when is this expression for y of t valid. First, let's just look at what we have for y of t. Well, in fact, we probably want to separate this into two different integrals. We have one integral where the red functional value is 2 and the blue functional value is minus t plus lambda plus 2. That's d lambda. And what interval, or what are my limits on the integration operation? Well, now the lower limit, I hope we can see, is t minus 4, and the upper limit is actually 3. But that's just a piece of it. We have another piece that has a different functional value for the red curve, and that functional value is -4. And the blue curve is still functionally the same. That's minus t plus lambda plus 2 d lambda. And now we integrate from a lower limit. Where do we have cross-hatching of red and blue? Well, that starts now in this pattern from 3 up to a value of t. And now we would just need to evaluate those integrals. But when is this pattern true? And you need to keep track of the width of the intervals of support. In this case, the blue width is 4, and the red width is 4 and 5 in terms of its intervals. So this pattern is true as long as t minus 4 lives between -1 and 3. So this pattern is true as long as t minus 4 is bigger than or equal to -1 and t minus 4 is less than 3. We also need t to be between 3 and 8. And some of these may be more constraining than others. But let's now say that t needs to be bigger than 3 and t is less than 8. Let's now see what we have. And we want to take the intersection of all of these constraints. This one, if we add 4 to both sides, we see that t is greater than or equal to 3. This one says that t is less than 7. And here, these two are actually consistent. So t bigger than or equal to 3 is okay. So this y of t expression is equal to something when t is bigger than or equal to 3 and the intersection of t less than 7 and t less than 8 says that t needs to be less than 7. So this, where this particular expression, maybe I should reorient that value. This expression now, when you evaluate it, would give you the functional form for y, and that functional form for y would be true as long as t lives between 3 and 7, and those intervals were determined based on this overlap pattern and the relationship between the endpoints of the blue curve and the red curve. We also needed to actually separate this y of t computation into two separate integrals because the functional form for, let's say, h of lambda was different during this overlap pattern. But I hope that this video now, talking about intervals and limits, helps you better understand or put together this convolution process.